Oh, hello everybody. Today I am gonna go do a few different circuits like I always do. The beer I'm drinking for this session is Zilla IPA from Rebellion, which is a brewery in Regina, Saskatchewan. It's very good. Um, so we are going to start with a what's it called? A diode clamp. Because, well, basically, I had a problem. It wasn't, well, I had two problems with the circuit I was testing today, and they weren't testing correctly. Add this diode right there. Draw, add wire. Well, first we'll add a voltage source. I'm actually going to delete this one. And we're going to draw inputs at two terminal voltage source. Yep, wrong way. This one. Add wire. There. Right there. And put some sources. Add ground. Ooh. So now, the way I anticipate this circuit will work is that if I raise this to above 5.6 volts, well, I actually still only apply 5.6 volts along this resistor because at that uh, amount, this diode will start conducting this way. Guess I should actually. Yeah. So let's run. So we got 5 volts here. This is at 5 volts. Now let's edit this. Put it to 7 volts. Apply. Okay. You see now we started conducting. Oh. Hmm. Add a resistor here. Hmm. So I am misunderstanding how a diode clamp would work. Let's just go clamper. I thought that must be, but I thought I had a handle on that. Ah, let's stop this here. Just see if I can get this to work right here. It only be. Diode clamp example. Let's see what this comes up with. Maximum clamp. In. No. I'm just going to move this over here. While I try to figure this out. Yeah, we go in. So let's delete this old one here. And I'm going to draw the circuit I found online here. Yeah, got the resistor. I'll go. Oh, hello, how are you today? Now we add. So what I'm making right now, supposed to be a diode clamp. We have the 5 volts there. I think I know. Because I misunderstood how the circuit sort of worked earlier on a different circuit I was working on. And now I just want to fix that, fix my understanding of that circuit. Basically, is what's happening here. And I think I did now. Yeah. That drops 5 volts. Now if we edit this to 7. Okay. Volts. That's still applying 7. Oh, oops. Control Z. Control C. Control V. And there. That's what I expected. So now if we go to 10. Yeah. So now I think the misunderstanding I had with my own circuit was just that you have to have some amount there. I wonder. Here, let's stop it. Just gonna try. I'm gonna put the resistor here and see if that does the same. Nope, still burns the full 10. Yeah, so it mostly goes through there. Edit. Go 100. Apply. Okay. Yeah. I think that's what my misunderstanding was, is that you have to have some resistance here. I need to look at the circuit that I had before, but that's where I was being confused. Because yeah, now if you see, I can raise this to say 100. Apply, okay. You see, it will all go through this 100 ohm resistor here, while this one has 5.8 volts there. I don't know. Does anybody have any other questions? I'll just say I was making a diode clamp. Yeah, it's an interesting circuit. I will move on now, I think, to the not filter circuits. Oh, I should stop here. Circuits, passive filters, not filter. So now I'm going to talk about a not filter. A not filter is it's a type of bandpass filter. I'm sure if you look here, I went to the Analog Devices website to get a sort of idea of what it is. And it says a not filter is a type of band stop filter, which is a filter that attenuates frequencies within a specific range while passing all other frequencies unaltered. So it looks like it like goes there and then it goes down and back up, like basically passes through some. So if you see here, let's just think about what we'd expect this to have. We got the inductor right here, which at a low frequency, right? You just think at a low frequency, it will let this output will stay non-attenuated. But at that same low frequency, the output will get attenuated by the capacitor, because the capacitor is going to look like a short circuit. So it's going to want that, and the inductor is going to look like a open circuit. So it's going to just want to pass it. And then vice versa for high frequency. At a high frequency, the inductor will look like an open circuit, and the capacitor will look like a short circuit. So, but they would have, like whoever made the Falstad simulator, which is a great simulator, would have picked this inductor and capacitor pair to pass like both of them, so that they would pass at a certain frequency. Let's run this and see. So you see we're slowly moving up. Our voltage out is going down now. Slowly. So it looks like it's a fairly low, like a low frequency which it passes. And now it's gonna be blocking it. Oh no, it's a higher frequency. Oh, my dog just let out a big sigh. Probably thinking, like, I could probably do this circuit analysis better than you can. Yeah, so it looks like this actually passes stuff between, like... Well, let's edit this thing. Go to 80. Apply. Okay. So now we'll just wait till we do one full one. You see here it's being basically blocking everything. Now it's letting stuff through. Oh, right, because, yeah, we're dealing with... Yeah, sorry. I forgot. We're dealing with one that blocks just a short band, so it lets through most of it. Yeah, no, my bad. So now we're at just the regular part, so it will let through that 20 hertz, and then it will start blocking around around 30 hertz, it looks like. So now we're basically blocking most of it. And then it goes right back and it stops blocking around 50. So that is this notch filter. Just takes out a... And I wonder if I can get a better sort of notch filter photo. Here. There's a nice photo, but you probably can't see it that well there. Now you can see it a bit better. So you see, you pass here, and then it stops it right in between right there. So you might do that, say if you were making something that you wanted to block the 60 hertz value, because, like, well, at 60 hertz you have, whatchamacallit, the like power mains are usually at 60 hertz. You might want to block that. So let's move on, unless does anybody have any questions? Again, for those of you who don't know, the beer that I'm drinking is a nice locally brewed beer in Regina. It's very good. It's from Rebellion Brewing Company. Let's move on. Oh, to long distance power transmission. Yes, I was quite excited when I picked this circuit. Other passive circuits. Is it in that one? AC circuits. Basics. No. Oh yeah, this one. Down transformers. There we go. This one. Okay, so this is long. What's it called? Long distance power transmission. As you can see here, this is a 60 hertz AC source. This is a transformer, 1 to 1000. So it takes this voltage here, bumps it up by 1000, and then this tamps it back down to, a regular voltage. The reason why they do this is something you'll be able to see soon, I think, from they have the voltage here and the amperage, and voltage and amperage. And the reason why they do this is that the voltage here and the amperage here, they are much, like the voltage is much lower, so the amperage is much higher. And here the amperage is much lower and the voltage is much lower. Or voltage is much higher. I mean, sorry, misspoke. And the reason why you would want to do that is if you look at the power equations, you have P equals VI. Then if you take V equals IR, you can replace it and you get P equals I squared R. So that means that you basically, if you can take this amperage and make it much smaller, you're going to have a much lower amount of power wasted along long distance transmissions. This is how we deliver most most of our electric power to homes, and it's the reason why AC run out versus DC. So let's start that up. You see here we're going from like, what is that, 100 and some kilovolts, so a very large amount, versus here, let's just slow the simulation speed a little bit here. Go down to like there. So we're going from like 160 kilovolts to probably minus 160 kilovolts, I would assume. And we have microamps here, whereas here you see we have amps. So this one right here, that resistor, it is wasting like a full, a lot actually. I guess it's calculating it as I hold it there. Sorry. Yeah, so 20 watts or so. Then here we are dealing with microwatts, which is good. Because you see, the thing is, if you look at there, we actually have 500 ohms versus that 10 ohm. But we have a much higher amperage. But that actually follows what we have in real life pretty well. Because when we have those long distance transmission lines, that resistance would be higher in some cases than our own wires, like in the house, because they're so much longer, which is why they crank up the voltage, because then you have a very small amperage traveling across those wires, and you therefore don't burn up as much power. The reason why AC is necessary is because of these transformers here, which can step up and step down the voltages. Then here, I think they're just showing like a house. I'm not sure. Yeah. So does anybody have any questions, comments, or concerns? Ooh. Any circuits that you'd like me to look at today? No? Well, we shall move on to relay toggle flip-flop. I briefly looked at this one earlier. Relays. Oops. Relays. Toggle flip-flop. Here we are. Oh, the app, it is... Here, I'll just put the link in the thing. It's called the Falstad Circuit Simulator. It is really great. Here. should give a Falstad was made. I believe that is a person, Paul Falstad, and it's this circuit simulator here, and it is great. I believe he's obviously just a JavaScript developer of some sort. I think it uses Circuit.js is what it's called. Circuit.js. Circuit simulator. Yeah. Ooh, that's even better. Circuit.js. Interesting. And yeah, so it's this guy here, Paul Falstad. That guy made it. It's great software, or a great website too. So this one now, basically, if we look, so if I toggle this, then it flips these two over. Yeah. Which then flips that over. Somehow it connects in here. Yeah. So if I flip this, then we'll flip that over. Flip this over. Which, let's just see. Yeah, so then it just clamps these on. Okay, I was looking to see if it actually would do anything once it got clamped on, but it looks like it just sort of doesn't do anything. But if we toggle this again, these are going to flip, because this will sort of de-energize this. And see, now we have stopped. So if we then hit this again, this will flip these down, and it will re-energize this, which will hold them where they are. See? And then that relay just basically holds it, and it will hold it forever because of the way it's wired, until we switch them, and that de-energizes them again. And yeah, now we would just stay like that forever. That's just with, I think they're just using electromechanical relays. It's what they would be saying they're using there. Does anybody have any questions with that one? I might, after, if I get through all of the ones I've planned out for today, I might just start freestyling, which those of you who were watching me earlier with the Diode Clamp might not appreciate that. Anyways, I think we can move on then. The next one is a differentiator. It's in the other passive circuits. This one here. So, this circuit's name sort of gives itself away. What we're going to see is a very what should be a close representation of a basically a differentiator. So something that takes the derivative of the input, which is this square wave generator. Let's just see if that's what happens. So yeah, we got, it's not a perfect one because you see it goes up, down, but it has a trailing off where it should just be basically infinity right there. Let's go, we edit this, and we do a triangle one. Go okay. Now you see what we have, we get almost a square wave on this side. Let's edit this, go do max voltage, do 100 instead. Actually, no, what we do can do increase the frequency. Apply. Okay. Oh, now we're really just freaking things out here. No. Let's go 50. Apply. Okay. You see what we get is a square wave looking thing, basically. Now let's edit this and we can try a sawtooth. So you see what's happening there now is that when we hit this point here, we get that attempt at like an infinity differentiate, but it can't do it. So then here we get 10.8 volts, which it's just trying to keep up to the change based on the frequency. I think this one is good too. Does anybody have any questions or comments on this one? Please, anybody who's interested, just send something in the comments. I'm trying to watch them quite closely. I think I will move on to the transistor switch. Well, my dog just groaned again. Oh, stop. So, now we're going to do this transistor switch, it's called. When we do this, when I flick this over, it's going to basically turn on this transistor. That's why it is called a switch in this scenario. And it's just wanting to demonstrate that you need very little current to turn on and off this load. Let's just run this. See, right now we have picoamps, so 500 picoamps going through, which is basically nothing. Now, if I go and I flip that switch, we will have effectively 5 divided by, so like a half milliamp, right? Yeah. Going into the base of this transistor. And that will be enough to turn it on to have up to, say, so 50 milliamps, because roughly the beta is usually around 100. Which we will not need that much to conduct the max through here, because this is 300. So let's say this is 5 volts here, and then we'll just go 100 ohms. If it was 100 ohms here, then we divide. The ohm would be 5 milli. It would be 50 milliamps, but then it's divided by 3, so it would be 50 divided by 3, 2.33 times there, say 20 milliamps or so. Let's flip that there. 16.3 milliamps. Now let's edit this. We'll just go down to 200. Apply. Okay. And 24 milliamps. We can keep on pushing it down until at some point it will stop because this won't be applying enough current to the base. Let's edit it and go 50. Apply. Okay. Yeah, so we've reached it right there, 43 milliamps. Apply. Okay. You see we're not changing at all. So I have one more circuit. Well, I think maybe more than one more circuit. Nope, only one more circuit I want to look at today. I've scheduled. So if does anybody have any questions for this circuit before I leave it? Okay. If nobody has questions, then we shall move on to our last circuit, which is a Schmitt Trigger. Transistors. Schmitt Trigger. Oh yeah. So, a Schmitt Trigger, let's go into the Wikipedia page of it. It's a comparator circuit with hysteresis implemented by amplifying positive feedback to the non-inverting input of a comparator or differential amplifier. Okay. This that's the output. This is one that I haven't really grasped very well again too, so it might be similar to how I was bumbling around with the diode clamp, of which I think I'm gonna make a video doing going in depth into the diode clamp, just because I obviously didn't get it well. I miss yeah, stay hydrated. I always stay hydrated. I love, well, I drink lots of water, but right now obviously I'm not drinking water. I'm drinking an IPA, which is it says here it's hoppy, citrus, tropical, and delicious. But it says, I'd actually just read this Understanding Schmitt Triggers sometime by Texas Instruments here. Obviously not right now, because here, I'll just give you this one. I'll go here. There. I sent some happy faces for the stay hydrated comment. Because I don't really have enough time to read it now. I probably should have before, but output. Yeah, so it takes the output back to the positive input, which is how I had read that there before, but this is the output here. Doesn't look like we're taking it out back to anything. Unless it's this one here. I think this is, yeah. Let's run this. This is the out right there. And I see, yeah, it's just using this 2 kilohertz to make some fuzz along it. And that's what a Schmitt trigger is supposed to do. It's what it's used for, is to give a little bit of noise resistance to your comparator inputs. Which, if you have been watching some of my videos lately, I have been designing a voltage comparator to just basically to learn more about comparators and circuit design in that respect. And well, that's the primary reason. The secondary reason is that I want to use it in Christmas decorations and stuff. It's actually by the coincidence, I actually have it right here. I don't know if you can see that well. So this is the PCB of it, and this is one of the earlier designs that it solely uses discrete transistors. But yeah, I might do another video too, just on the Schmitt trigger after researching more, either on like reading this Texas Instruments application report, or just playing around with circuits on my bench. Probably a combination of both. Anyways, I think I am done for the day. Now, that's the circuits I had listed that I've went through. Yeah, I'm still not done my beer yet. But if anybody has any questions, then feel free to ask them about this circuit. Otherwise, I'm going to pick one at random to finish my beer with. And after that, I am going to go to the hot tub and have another beer, but in the hot tub. And that won't be live streamed. You guys don't need to see that. It's not very fun. Okay. Let's just go in here. Op amps. Let's see what a full wave rectifier for op amps looks like. What is going on here now? I haven't looked at this circuit. I just picked it from random, like I had said I would. So, this is the output. And yeah, it's nice full wave rectifier. What is the max voltage? Wow. That's why you would use a op amp. I can see right away. You're getting basically that whole volt out, whereas in a regular full wave rectifier, bridge rectifier, you would lose about a volt. So that's very interesting. But let's just analyze what's going to happen here. Maybe we'll stop this, reset it, and then we can look at it with sort of fresh eyes here. So, say that we have a positive 1 volt here. It's going to go through here. This will be higher than what this one is. So we will actually start outputting enough voltage such that this will cancel, so no current will be flowing this way. Right? Yeah. So that would be, if we had a volt here, we'd want to eliminate this. So we would want to be outputting. Let's just think here for 1 second. We have 1 volt here. We want to get this to actually 0 volts. So we are going to basically throw it all the way up to its negative rail. That's not what it's doing. Let's slow this down some. That's microvolts, millivolts, microvolts. Oh, I see what's happening. So if we have a positive voltage here, this, now we have negative voltage, but we had a positive voltage for a while. But if we had a positive voltage here, then this would go here, and then it would want to see, I don't really know anything about digital or analog circuitry. Why are electrons flowing into the 500 ohm resistor from the left and right 1 kilo ohm path when it oscillates? I'm not sure if I understand your question, but this, while it is the electrons flowing, this is more just symbolizing which way the current is going. So right now, so you see it's flowing this way. That's because there's a positive voltage coming through here. And the way op amps work is there's some golden rules. Here, I'm going to just stop this for a second. They're called the op amp golden rules. And what they say is that these two inputs want to be equal. That's their goal in life, is that there wants to be 0 volts difference between them here. And no current flows into the inputs. Those are our golden rules with op amps. So when we apply a positive single volt here, well, this will actually want to cancel it out. So it will output enough voltage that there will be a current flowing through here that will cancel out that volt. So to make this 1 volt, or to make this 0 volt, yeah, so no, that is just 0 volts there. So this is just a virtual ground. So that means that we would have. Why does that not make sense? Okay, I'm still confused about it. We're gonna just go back here, and I'll just say when a single volt is here, then this will be conducting at half a milliamp right there. I guess I neglected this here. So anyways, it will conduct into here, and then it will this will have a volt, but this also wants to be at ground. So we will be again going through here. And then this will be at 0 volts effectively. And it will flow back through. But how does that affect this? Hmm. I don't know. I think I'm sorry, Hunter. But at this moment, I don't think I have a good answer for you. I'll just type that out. It basically, uh, like if you've noticed through this video, I'm one of the reasons, like I have dealt with a few of these different things, but one of the reasons why I'm doing these videos is that I'm actually trying to learn them more, and I'm sort of checking my knowledge because I'm learning on my own. And one of the best ways I find to check my knowledge is to sort of put myself out there and try to just explain it in simple words. That's also why I hesitate to do any math that I can't do in my head. It's sort of a uh, a a instead of having like coworkers that I would talk to like around the water cooler about this, I just do it on video here. But anyways, thank you for all of you for coming. I think I'm going to cut this off unless anybody has any other questions like Hunter did. Again, like my uh just to the guy who told me to stay hydrated. I did this time with this beer. It was very nice. Um, I should talk to those breweries and see if they'd give me free beer for talking about them on these live streams. But yeah, other than that, I think we are good to cut it off. Thank you all for coming.